Thermodynamic review. So thermodynamics in Chinese is 热力学. Okay, first, it's delta L is equal to 1. Delta L equal to alpha L 0 times delta T. So this is so-called the linear expansion. Yeah, expansion in Chinese is 膨胀. Okay, and alpha here is coefficient of linear expansion. In a unit, you can see alpha and delta T, they must cancel out because L and L0. So it must be 1 over degree C. And if the delta T degree, so delta degree C and delta degree K, the number is the same. So it doesn't really matter. So delta L is the expansion amount, right? Expansion amount. And L0 is the original length, right? So L0 is the original length. Two, delta V, volume, is equal to beta and then V0 delta T. So this is called volume expansion. So volume, it's Tg, right, in Chinese, Tg. So same thing, beta is the coefficient of volume expansion. Coefficient of volume expansion. And the unit, so the beta I need to cancel out this delta T. So that's 1 over delta C again. And C is Celsius, right? So C here is Celsius. So in Chinese, that's 摄氏. So that's the scale of temperature, right? So next, we're going to talk about the different gas law. So first, number 3, we're going to talk about Boyle's law. So Boyle's law says PV equal to constant. PV, so pressure, this is pressure. So pressure in Chinese is 压力. And V is volume is equal to constant. So this also means that P is equal to this constant divided by C by V. So that means that P is proportional to 1 over V. Or you can say P and V are inversely proportional. Inversely means, you know, like a 相反的, right? Inversely proportional. Okay, so that's Boyle's law. If you can keep, so here you're assuming you're keeping N, so that means the number of mole, right? Number of mole. Mole in Chinese is more, right? So that's a unit of molecule, right? Number of mole and the T are kept constant. These two are fixed. In that condition, then this is true. Number 4, I'm going to change in color here, so we'll make a little more obvious. Number 4, it's going to be Charles' law, right? It's going to do Charles' law. So Charles' law says that V is proportional to T. Okay, if you keep N and P constant, then they are proportional, right? So V and T are proportional. And number 5 is the Gay-Lussac's law, right? So Gay-Lussac's law. So this is a little less familiar. And this one is between pressure and the temperature, right? Pressure and temperature. So if you can keep N and V constant, N and volume constant, and N is a number of mole, right? Keep them constant, V and N constant. So then that means pressure and absolute temperature, right? So all this here, this T here, you need to write, this is okay. The delta, this can be in delta C or delta Kelvin. But this here, this T here, and this T here, they need to be in absolute temperature, so degree Kelvin. So it was derived in terms of degree Kelvin, so you had to do that. And if not, all the number doesn't. And this P is in terms of absolute pressure, so absolute pressure. So absolute means 绝对的, right? In Chinese, 绝对的, right? 绝对的. Okay, so that's number 5. And now we're going to go to the ideal gas law. Okay, we're going to go to ideal gas law now. So that would be number 6. So number 6. So basically you put Charles, you put Boyle, and then you put Gay-Lussac, right? Gay-Lussac. Right, all these 3 laws together, then you have the ideal gas law. So it says that P times volume, pressure times volume, is equal to N R T. And this N again is number of mole. And R is the universal gas constant. So in Chinese is 通用. 通用 means universal. 通用. 气体. 气体 means gas. 通用气体常数. So universal gas constant. And this one here is equal to, R is equal to 8.314. This is the one that in terms of SI units, which is the unit is joule divided by mole, and this has parentheses, mole, number of mole, and then you have the K. Okay, so that's the unit of that. And N is number of mole. You can see that will cancel out. Then you have this joule. This is joule, right? This one here, joule, energy unit right there. So, and this again, this is in absolute pressure, right? So absolute pressure, as you recall, is equal to the atmospheric pressure plus the gauge pressure, okay? And this is volume, right? So this unit here is N divided by meter square, and this unit here is meter cube. I want to change color here. So these two together, you can see it become Newton meter. So that's equal to joule right there. So you can see P times V give you the energy, right? They are in the energy unit there. And this is mole. The mole cancel that mole right there. So your joule and degree K. So degree K and degree K cancel this degree K right there. So then just joule equal to joule now, right? So this is degree Kelvin. Right, and this is the scale, right? The temperature scale. right, for Kelvin, right, or absolute, right, absolute temperature scale. Okay, so that's that. And then we're going to introduce the so-called the additional equation here, the different form of ideal gas law. So this is the different form, E-R-E-N-T, right? So I'm missing an E-N. Different form, right, of PV equal to nRT. So it's quite simple. So PV equal to nRT, N is number of mole. That's equal to the total number of molecule. So N is the total number of molecule. I'm going to change the color again. Total number of molecule. So molecule in Chinese is 分子, right? And divided by the Avogadro's number. So N capital A. So N capital A is Avogadro's number, which is 6.02 times 10 to the 23, and that there's no unit there, it's just the number. So then when you divide them together, oh no, this is the number of molecule divided by mole, okay? Number of molecule divided by 1 mole, okay? I misspoke. So then when you cancel this number of molecule, then this one flip, then become, this is the number of mole right there. Okay? And this is called Avogadro's number. A-V-O-G-A-G-A-D-R-O, D-R-O, comma S, right? Number. Avogadro's number. So that's just a person's name, Avogadro. Okay? Now we're going to substitute this one into here, and you will see then this one here can become N divided by NA, and then you have an R right there, and T. And now this, I'm going to change the color again. This, it can be called a Boltzmann constant right there. So that's equal to K. So little k, not capital K, which is equal to N, K, T. And K is equal to 1.38 times 10 to the negative 23 in joule divided by K. Okay, sometimes say degree K, sometimes no degree. Okay, but Boltzmann constant, B-O-L-T-Z-M-A-N-N. Yeah, I think N-N means it's a German last name. Okay, Boltzmann constant, 鲍兹曼常数. Okay. All right, so then we're going to talk about next one, number 8. So number 8, going to talking about the kinetic theory. Right. So the main results of kinetic theory is that Ke, going to change the color. This is not too clear. Ke average, and this one here is the average translational. So obviously vibrational is also important, but translational has the most of the kinetic energy. Every translational kinetic energy, right? The bar there is average, but here is also only for the translational, which is equal to 3/2 Boltzmann constant times the absolute temperature. So what does that mean? It means that every translational kinetic energy is proportional to T. Okay, so the higher the temperature, absolute temperature, and this T has to be in the absolute temperature. Okay, and Ke here in Chinese is 动能, kinetic energy. Right? So they are linear proportional. So this is, you say Ke. So in English, you say Ke and absolute temperature are linearly proportional. Right? So linearly is the adverb, right? And that kind of modify the proportional, which is an adjective. So this is a very, very important result. And so hopefully you can make good use of it. And next, we're going to talk about the Maxwell distribution of speed. So Maxwell distribution of speed. Okay, so that one just says that relative number of molecule here. So relative number of molecule will change in the different temperature with respect to V, which is the speed. So if you have temperature, let's say equal to 0 degrees C, for example. So this is Kelvin is equal to 273 degree K, right? Of 0 degrees C, which is 0 degrees C, 0 degrees C, Celsius, Kelvin. And when the temperature becomes higher, it means that you have more molecule, right, in the higher speed, okay? So the higher speed, so if you look at this speed here, which is on the higher side, this number will not be this value, which is, so in before you have this number here, right? The number of molecule at this speed, right? It's right there. This is some kind of n right there for this particular speed, say V1, right? So you have the N1 right there. So then when the temperature increase, this number will increase. So now instead of that one, it will have something like that, for example. Okay, so then at the V1, now instead of N1, now you have, right there, and that's your N1 prime, okay? In this temperature, the new temperature, T prime, is equal to 303 degree K, or it's 30, right? 30 degrees C. You can see, so you shift the distribution, you have more higher, so this one has more higher V molecule, right? More higher V molecule. So more molecule traveling in higher linear velocity. So that's the Maxwell distribution of speed. When you're changing temperature from lower temperature to a higher temperature, it's shifted to the right. Okay, so we're gonna stop there, and that's all we have. Keep watching and keep learning more physics.